Hello.
Yes, sir.
Hi. So, yeah. So I have not posted any new video. The reason is that whatever. So I thought that I will try out mm, a new strategy. So what I will be doing is that I will discuss. So particularly whatever we are going to discuss today, that would be a bit more technical than what we have seen till now. So it will be better if I kind of present it to you guys here, and then instead of doing a video, I have already in the web page given links to some nice write-ups, because that might be easier for you guys to follow than the video. So, so we will have a discussion uh, on the analysis of quicksort, which we kind of started last time. Uh, but yeah, before we start on that, please let me know any questions, doubts that you have from whatever has been done till now.
Sir, in the problem set,
Yeah,
practice problem set,
yeah,
we had to solve some of the recurrences.
right,
So, like especially the ones involving log n,
right.
I had problems with them, and the rest of them I was able to solve, but they were way too long. Like took a lot of time to solve.
So what do you mean by solve?
Like we had to exactly solve. We had to find
No,
a cluster.
no. See, again, this is something that I had kind of intentionally kept it ambiguous. See, whenever you are given these recurrences, okay, I mean, it is like the best that one can hope for is to get it exact, okay, but that is something that is doesn't happen regularly, okay. So if you cannot do that, then the next thing would be the best thing is to prove that it is asymptotically similar, meaning which is that this limit of an by bn is goes to 1. Okay, that is the next best to exactly solving it. And then the third one is basically on if you can't even do that, then the next thing will be for trying to get a theta notation, right? So what is the theta thing that you can talk about? And then if you can't even do that, then you can go into things like, okay, I can have a upper bound of order and a lower bound of omega, and maybe these two are not tight, but that's fine. Okay, so whenever these recurrences will come, see again, I mean, I don't think we will be asking you this kind of questions at all in your exam, that how it solves this recurrence or something. But there will be algorithms where you have to find out the running time, and then of course, if you can do it exactly, that's wonderful. But if you can't do it exactly, if you give a theta notation or something like that, that's also fine. Okay, so it's up to you. So with many of these recurrences with logs and all, I also don't know whether there exists any exact bound. But I think you can get at least theta notation. You can almost certainly get, and if not theta notation, you can. I mean, you can do something. For most of them, you can do even asymptotic.
So asymptotic, all of them were done. Just D and E part I couldn't solve exactly.
Yeah, that's fine.
Asymptotic was easy.
That is fine. That is fine. Yeah, I mean, in most of the times, finding it exact can become very complicated. I mean, of course, I cannot say that it cannot be done, but they can be very very long. Okay. Any other questions? On whatever has been done so far? Nothing? Okay. So let me then, I mean, if you don't have any questions, let me go into the whatever we are going to do today, which is basically we will be analyzing the quicksort algorithm. So maybe I will share the screen. Do you see the screen?
Yes.
So we will be doing this. So this is the analysis of quicksort. recap, what is quicksort, right? So what we have to do is that we have been given this. So you have this array, right? A, and of course there is this. So you pick any. So pick a random I. Okay. When I pick a random I, if I don't specify it anything, you can say that random I is like uniformly at random from 1 to n. Okay, from 1 to. Then the next thing is that partition A into basically 3 parts, right? 3 parts. What are the 3 parts? So this side will be, so there will be something which is A, which is less than AI. So all of the elements such that, so these are all these J such that AJ is less than AI. Then there will be an AI, and then there will be the ones which are all these maybe K such that AK is more than AI. In fact, I mean, actually, it should not be J and all, right? It will be AJ kind of stuff. These are all actually all the AJs such that these are this, and this is also these AKs. So we partition them into 3 parts, right? And then we recursively simply sort this one. So let's call this one A less than I, and this one A greater than. And we don't have to really worry about putting them together because they are all kind of together, right? Somebody has sent a chat or something.
Sir, I sent it by mistake. I sent it to everyone by mistake.
Okay, okay, okay. Okay, so is it fine? So, okay, so this is the analysis, right? This is not analysis, this is the quick sort. So, any question about that? No question? Okay, good. So, I am not writing the pseudocode of this quick sort exactly. Since we have already seen this pseudocode of the merge sort, you should be able to write the pseudocode of the quick sort. The more interesting part is that what is the analysis of runtime analysis of quick sort, right? So how do you do a runtime analysis of quick sort? This is something we did in last class in some sense. So let's say that the Tn, like in the case of merge sort, Tn be the runtime for quick sort on array of size n. Right. In that case, in the case of worst case, the issue is that these two arrays, they need not be half and half, right? They can be, in the worst case, they can be very skewed. One of them can be 1 and one of them can be n minus 1 minus n minus 2 kind of stuff, right? Right. So in the worst case, all you can say is that T of n is equals to T of 1, because one side is 1, plus T of n minus 1 minus 1, so which is T of 2. And of course, we have to partition them. We have not gone into the details of how do you do the partition, but this is order n. Right? And this one, if you solve it, what you will end up getting is order of n square. right? So this is the worst case runtime of quicksort.
So what is the ON term over there?
The ON term is for the partition, right? Is this one. When I say that partition the A into 3 parts, how do you partition it? Right? This is you have to go over the array completely, find out which elements AJ is less than or equal to AI, and kind of move it in this initial half. And for all those cases that AK is more than AI, we move it in the later half. So this partitioning will take order n steps,
Okay, sir.
right? Yeah, so it is not the merging. It is not merging. Merging is not costing us at all. Okay, merging is not costing us at all. There is no merging thing. But it is the partitioning that is kind of coming in the picture. But also one thing that I should kind of point out here, maybe this is something we discussed in the last class, and so this partitioning can be done in place, meaning there is no extra memory that has to be used. You can go over this array, and while you are going over the array, then you can start moving things accordingly and get everything partitioned into this A less than I and A greater than I and AI. Okay, so this is kind of important, and this is what is the most important or interesting part of quicksort, that it is in place. So which means that it is not using any extra memory. Okay, so this is better than the merge sort. But the problem is that, okay, the memory, we are not using any extra stuff. That is fine. I mean, although I have not exactly given a formal proof of that, but you can convince yourself and prove it yourself that in this quicksort you don't need any extra memory. But the worst case running time is becoming too large, right? So the thing that we need to do now is not
Sir.
the worst. Yeah.
Are we assuming that in the worst case, the element has one element on one side and n minus 2 elements on the other side?
I mean, it can be, right? You can be something worse also. If you think that there is some other ways of doing it, oh, that's maybe
We
a good
can
point.
have a corner element.
So it might, okay, good, very good point. So this is actually, in some sense, this is TK, okay? So let's say that this is the size of this set, say, okay, this set, the size of this set is K, okay? In that case, what we have is that this is Tk plus T of n minus, so n minus K minus 1, n minus 1 minus K plus order n. Okay, so this is what in general will come out. Oh, I kind of skipped a step there. Okay, so this is all you can say. Where the K can be any number, I don't know. Okay, so K can be any number. Okay, so this is what you have, that there exists a, so how I partition it is that there is a K is a number that is strictly less than n, and that's all we can say, right? Oh yeah, sorry, so you are right. So I think this is what we are meaning. Yeah, I think the worst case would be not T of 1. You're completely right. So I should kind of change it. Worst case will be the case on T of 0. So one side K becomes 0 and the other side becomes n minus 1. But again, it doesn't matter. Both of these things will end up giving you n square, order n square. Okay, so this is the, in general, how it will be split. Right? Now, okay, any questions?
No, sir.
No. Now, what we are interested now is the, okay, this is the worst case, but look at our quicksort. There was a kind of a randomness there, right? Which is a pick a random I. And you guys are all students of statistics, right? So you know that randomness, when you do randomness, it is rarely always, I mean, the Murphy's law doesn't exist. It doesn't apply in randomness, right? I mean, it should not be that always you get the wrong or worse setting. Correct? So in that respect, a natural question would be that what is the expected runtime? Expected runtime. Or in other words, what is the expectation over T of n? Right? So what is this quantity? Fine. And this is what we are interested in next. That okay, fine. Your worst case runtime is n square, and what is the expected runtime? Yeah, somebody wanted to ask something.
Sir, yes, sir. Sir, even before that, like, without knowing the nature of the function t, how
Yeah.
can we ascertain that for what k there will be a worst case, right? Let's say, for example, if let's say t was linear, let's say some proportional to the linearly proportional to the size of whatever it is sorting. In that case, for whatever k, the time would be equals, right? Because k n minus k plus 1 splitting.
Order
Sorry,
n.
it will.
The order n.
No, sir. What I wanted to ask was like, how will you, like, without knowing the nature of t, how do you ascertain that this is okay for k equal to 0? This is the worst case. How do you
Okay.
prove that?
Good. So I will leave it as the exercise. Okay, this is something that you can prove that. Okay. So one thing that you can assume, this is something slightly maybe that t is an increasing function. So that is one thing that you might be able to assume, but even that is also not required. Even if t is, I mean, t is a positive function, it always outputs a positive number. And that's all that is need to prove that if you have this one, this is the worst case that will happen. Because we will see it in a bit later on, what happens there. Okay. You see. So for example, can you think of a k for which this is not p n square? So if I say that every time you do it, you will k will not be, you will be k some number.
By 2.
N by 2. Okay, so if k is always n by 2, then it is of course not n square, right? Then it will be kind of the mod sort, which is n log. But anything else? Is n by 2 kind of very essential?
It can be n by 3, n by 4, but
It can
something
be n by 3, n by 4. So if you can somehow say that, oh, see, for all the time, somehow so somebody came up and told that, okay, see, I have done this quick sort, and do you know what happened? Magically, every time I do it, this k was actually between n by, say, n by 3 or n by 1/4 and n by 4 and n 3n by 4. Right? In that case, what can you say? Every time k is between, so say, so this is something I will ask, okay? What if, I don't know who can guarantee us, a God guarantees us, that k is between n by 4 and 3n by 4. It can be any of them. Then what is T of n?
order of n log n.
Right. So there is, so there are two ways of seeing it, okay? This is the order of n log n. Now, how do you prove it? So the one way of proving it is actually to kind of, okay, it's like I mean, just like here, it is, you can solve it by induction. That is one option. Okay, always you can prove it by induction. The induction always guarantees that. And another way of seeing it is that what is the largest size of the array? So this array is getting split up into two parts, right? So initially it had n, then it got split up and into two parts, right? And I am guaranteed that k is between n by 4 and 3n by 4. So I can at least say that the largest of these two arrays is how much? Is 3n by 4? Because even if it is n by 4, the other one is n minus n by 4, which is 3n by 4. So you can always kind of prove that every time you apply this one partitioning technique, it would go down by a factor of 3n by 4. Okay, so the next time you do it, it will become 3n by 4 whole square times n. And you continue like this. So it's kind of the tree, right? So if you think of it, this was the array A, right? Now this array A got split up into two parts. One is array A minus less than I and array A bigger than I. In the next time, it will get split up into another two parts, right? The array A less than I will get up into two parts, maybe related to J or something, and this will come up with related to K. Right? So this is the kind of how the recursive algorithm will keep on working. So this is how the first step of the quicksort, first step, or the first recursive step. And then you apply quicksort here, and this is the second recursive step, and so on. Now, question is that what is the runtime? Right? Runtime is the total number of nodes in this whole path, whole tree. Right? Not the nodes, actually, every time you split it. So this will take order n steps. Like there is the order n steps to split A into two parts. Now there is an order k here and order n minus k here. So forget that minus one part. But let's think of it this also. So every step, every layer, the total amount of time required to split this, split this one into two parts plus splitting this one into two parts, total times taken is order n, right? Because this will be order k and this is order n minus k. So total is order n. Similarly, when you split up into two parts here, right? Maybe one of them doesn't get split up because it has kind of stopped or something. So total time taken for splitting up this whole thing slowly into parts, how much time is it? It is also order n. Fine. And question is that when does a particular object stop? When don't we split? I don't split when the size of the array, right? Size is equals to 1. There's nothing to split. Right? When the size is 1, I kind of stop. Ah, okay, good, I got it. I mean, there's only one bit. So, if I can guarantee you that at every round, the maximum size of the array in each layer, okay? So this is a layer. So in each layer, so layer 1, what is the size of the array? It is at least at most 3n by 4. What is the size of the array here? It is 3 by 4 whole square times n. What is the size of the array here? Maximum size. Okay, maximum size of the arrays in this layer will also be like it will go down to 3 by 4 whole cube times n. So in other words, the after how much time? Note here, this is by 4 by 3n, right? After 4 by n steps or layers, I will not say steps, like layers. The 4 by n layers, what happens? After 4 by n layers, the maximum size is equals to 1, which means that the total depth meaning the number of longest paths from the root to the leaves. Total length of the tree is equals to less than or equal to log n by 4, right? So what are the number of nodes? Okay, so rather what are the runtime? What is the runtime in that case? See, this is the total layers. Okay, number of layers is 4 and 4, log n base 4 by 3. And each layer takes order n. So this will become order n into the log n base 4 by 3 is basically order log n. 4 by 3 is the constant. So it is also order n log n. Okay. So that means if I somehow guaranteed that k is between n by 4 and 3n by 4, we can guarantee you that T of n is at most n log n. Okay. But it is similar argument. So whoever asks that how can you guarantee that this is the lowest, this is the best, I mean this is the worst case in this thing, you can do it in the similar way. Okay. You can use the similar tactics by drawing a graph and try to convince yourself that the worst will come there, and in that case it will be order of square. Okay. Okay, good. Now we have picked, okay, any questions so far? This is a very crucial observation, by the way, that if this k was between n by 4 and 3n by 4, I would have been, I mean, it would have been split up into two halves, which are equal size, or not equal size, which is the comparable sizes, and which means that the total runtime would have been n log n. Any questions so far? Hello.
Hello. So, hello.
So do anybody has any suggestions about how to go forward now for the randomized, so the analysis of the randomized algorithm?
Hello.
Hello, can you hear us?
Yes, sir. Sir, I had a question.
Yeah.
So, in this case, on the right side, I have a constant n. Right. So my recursive equation is T of x is equal to T of x by 4 plus T of 3x by 4 plus n. Right.
Right.
So which intuitively gives us that this should be order n log n.
Right. Intuitively gives us, and this is how I kind of gave you the proof also, right?
Right. So in here we have the proof, but in case the constant was n square.
Instead the constant was n square, right? So then that will be a bit different. Then that will be a bit more complicated, because every round, like I kind of told that in each layer it is order n, which is because it is order k plus order n minus k. Order k plus order n minus k is basically order n. But order k square plus order n minus k whole square is not necessarily, I mean it is still order n square, okay, but it can be much lower than that.
So the end product, we would not expect it to be order n square log n.
I mean, it will be order n square log n, but it might be better.
Because like I tried writing the question in the code, and it turned out to be order n square only, rather than n
It will
square
become
log n.
order n square. Because as I told you, I mean, it will be order n square log n, meaning it will be lesser than n square log n. Okay, but it will be better because see, after the few layers, I mean, like this is order k square plus order n minus k square. Okay, and similarly, you can keep on going down. After the constant number of layers, you will see that all you are producing is order n.
Okay, sir.
Okay, so it is, so this is if this was n square, right? Yeah. But since we have order n, so we have no problem because order k plus order n minus k is actually order n.
Okay, sir.
Yeah, I am kind of assuming here the orders have the same constant heat hiding, and that is because of the algorithm that you kind of we do same algorithm will be applied, right? So number of steps required to maybe partition it is 2 times n or 2 times k plus 2 times n minus k, which will be 2 times n. Yeah. But now, you guys tell me, you see any way of understanding why, how can you analyze the randomized algorithm? So what is the expected value of T of n?
So my probability of picking n in the middle half will be 50%.
Hmm?
So 50% of the time I will have n log n steps.
Right.
And in the rest of the times I'll have something bigger than n log n, possibly n square steps.
Right. So good. So see that if I had the guarantee that every time k is like this, then we would have got n log n. But do we need to have it every time? The idea is that, so consider a particular path, any path. Okay, for a, once I have a path, right, it will going down, right? The size of the things are going down, size of the arrays are going down. Okay, now so let's consider this one a bit more formally. Let's consider the size of the array containing the element, I don't know, x. Okay, so x is some element in the array. I don't know what is it, but I'm looking at the size of the array that contains the element x. Okay, so initially, what is the size? So maybe let's define it like this: that Si x is the size at layer I. Fine. I'm just looking at particular x, right? So say maybe at the end of the day, x is here. Okay. Use it a different color. So x is here. Okay. So I'm looking at this path, right? So what do I have? I have that you initially had S1 of x, which was the whole set, and this is equals to n. Then next time it happened what? Okay, it got split up into 2 parts, and it became S2 of x. It's something smaller than S1 of x, I know that, but I don't know anything more than that. I cannot guarantee you anything. Then similarly, S3 of x and so on, it goes down. Right? Fine. Can you hear me, or can you hear a disturbance from the background?
There is some disturbance, but we can't hear you.
I don't know how to do it. Some construction is going on here. But am I audible?
Yes, sir.
Okay, fine. Okay, so there is this thing that comes on, right? Now say maybe the first round, okay, it has just gone down by a little bit. Okay, it has just gone down by a little bit. So this is say equals to n minus 2. Okay, much can be done. But in this round, the K that was chosen managed to split it up into something so that it is of size 3n by 3, 3, 4, 10. Like this goes on, right? So it means that if that happens, every time this splits up, so let's call this one good, okay? Let's call this one a good splitting. So if a good splitting happens, right? When do a good splitting happens? This is when K, you remember the K that we had talked about, was between n by 4 and 3n by 4. Okay, now this n is changing, by the way. N, I mean n of the array on which we are splitting up, which will change. Okay, isn't consistent with that? Okay, so every time a good K is chosen, it gets split up and the size of the array goes down by a fraction, a constant fraction, right? So what does it mean? It means that if by the same analysis, right, how many times can you go down? At most log n. If we pick something like order of n, and now I'm not, so say maybe just forget order of n, I will write it exactly. So log of n base 4 by 3 good K, then the size of the array, size of array containing x will become 1 and will stop, right? Fine. So if we pick this one log n by 4 third times, we will become, with this whole tree or whole this whole path that we talked about will come to a stop. This is just one path we are talking about. Okay? So that means how many times to the quick sort gets applied to an array that contains x? It would be number of good ones. But what is the probability? So what is the probability that K is good? Now think of it, okay? So think of the ordered one, okay? So I'm talking about the ordered array. A. So ordered array is, say I would like the A1, A2, A3, so A1 is less than A2 is less than A3 is less than AN, right? Now look at here, there is a place here. So I will be picking up a random K, right? So K is somewhere here. And once whichever K I pick up, so K is not here, okay? So this is, I should say, not a K. This is basically, so in the original one, I have picked up a random I, right? It is the A of I, whatever that A of I is. I don't know what is A of I. So this is A of I. A of I is randomly picked. So I is randomly picked, that means A of I will be randomly picked from this whole set, uniformly at random, right? And if this A of I is between the n by 4 and 3n by 4, then we are in very good shape. Right, we are picking up a random I, which means that we are picking up, because I don't know the ordering of A, right, initially. So I'm basically picking up a random element from this whole set. And if the random element is within this range, I call this one good. If the random element is not in this range, I don't call it good. So probability it is good is this size of this range, right? So this is equal to half, right? So what do I have? That expected number of expected, let me put this one. Expected length of the path containing x. What is it? I know that if I get this log n base 4/3 number of good ones, my game is over. And I get it with probability 1/3, probability half. So that means if I do 2 log n this 4/3, I'm done, right? If this many number of, if the length is this much, that means I have applied this, chosen a random pivot this many number of times. Half of the times I expect it to kind of partition into 2 nicer halves, right? And in that case, that means this total length. If this is the length by expected length, by that time my size of the array should come down to 1 and my length should stop, right?
Sir,
Yeah.
instead of the equality, isn't there should be a less than equal to?
Which one? Which one?
The expected length of the path containing x, the last line.
Yeah, there will be less than equal to. You're right. Okay. Yeah, I mean, since we are only interested in the upper bound, so I was not really worried about the less than or equal to or equal to. So that means this is for any x. And by linearity of expectation, you know that, right? It's not a linearity of expectation. It's kind of this for every I, this is the expected length. So what is the expected depth? So the expected depth is order log n. So the expected value of the T of n is order n log n. Okay. Any questions? Any doubts? Okay. If not, I can give you something more. What can I give you? Now, I talked about this concentration inequalities and all, right? The expectation is just average. Okay. So if I say that the average of this class's marks is 50, or I say the average of this class's marks is 50, will you be happy with it? It is not very illuminating, right? It might be that 50% of the people have got 100 and 50% of the people have got 0. So that is average, or expectation is never a very good indicator of the random variable. But if I can tell you this following fact, that with high probability, okay, or probability that a person has got between 40 and 60 is almost 1, then you are kind of understanding what's going on. Oh, okay, good, good. There is a lot of concentration around the expectation, around the average, right? And this is what we call as concentration inequality. So like here we wrote that the expected length of the path is this much. Good, that is completely right. But I want something more. I'm greedy. I want to say that, yeah, sorry. Sorry. I don't get you. Can you repeat?
Sorry, sir, there was some background noise.
Oh, okay. Okay, so we want to say something like this. What is the probability that the length of the path, okay, here I mean containing x, containing x, okay. Now I know that this is expectation, right? The expectation value is this number, right? But what is the probability that this is more than 2.5 or maybe something else? Maybe I'll just say, okay, fine, it is expectation, but it is, what is the probability that this is more than, yeah, so let's say 2.5. 2.5 log n is 4/3. What is this quantity? I want to say that this quantity is very, very small. Okay, this is less than 1/n square. This is what I want. Okay, so I want. You see that this is a much more stronger statement than just expectation. So this is saying that what is the probability that our random variable, which in this is the length of the path, what is the probability that the length of the random variable is, sorry,
না চলছে
So background.
চলছে না বলছি তো
Aditya.
okay, okay, fine. So what is the probability that the length of the path is close to the expected value, right? Which is this. Expected value was 2, and we are just wanting something more. And if we can prove that this is less than order n square, okay, then what happens? Then what can we say? If we can prove this, okay, I have not proved it yet. But if we can prove it, then see there are at most n of this x's, right? There are at most n of the x's. And in that case, we know that every x, what is the probability? So then we can say that probability that the depth, now depth is for all x, right? So depth meaning, so this means that all length of all paths is is less than 2.5 log n by 4/3. This is by union bound. This is less than 1/n. So, sorry, this is less than, sorry, this is more than 1 minus 1/n. Now I have jumped a few steps here. Now I am, please tell me that, whether I should repeat these steps or not, because this is the union bound and all of them. But since you guys are coming from statistics world, I was assuming that you are comfortable with this kind of analysis. Is it fine? Is applying the union bound?
Can we explain again?
Can we explain again? Okay. So this is something I have not proved. Okay, this whatever is written in the red box is I want thing. Okay, so let's say we somehow prove it. I have not told you how to prove it. I will tell you. But if you prove it, that this is, what does it mean? It means that what is the probability that the length of a single path, or probability of path containing x is bigger than 2.5 times log n, is 1/n square, right? So this is an event, okay? So this is if I call this one an event, okay? So the event EI is that length of the path containing X is more than 2.5 log n base 4 by 3. So this is the event, right? And I should not write it EI, right? I should write it as EX, this EX. And now we want, okay, so EX is a bad thing. Okay. EX is a bad event. I want to control EX. What is the probability of EX? And what this statement says there is that probability of E of X is less than 1 by n square. And what we are interested in is that what is the probability of, I mean, what's the bad thing? Bad thing is that the depth is bigger than this one. That means there exists some X for which the length is bigger than 2.5 times log n base 4 by 3. So this is, what is the probability of union of EX? Right? And now this X is basically, there are n of them. So this is therefore less than 1 by n. So that means that this is only this much probability that someone, for some X, the path is bigger than this quantity. So, which basically means that with probability that all paths are less than or equal to 2.5 log n by 4 by 3, this is more than 1 minus 1 by n. So this kind of stuff is just the union bound. You guys are familiar with union bound, right? I hope. Hello.
Yes.
Yeah. Okay. Fine. So this is what we can have. So see this statement. No, of course, I have not told you how to get this red statement, red thing here. But if we can get it, look at this statement. What does it mean? Think of n to be equals to 100 or n equals to 1000. Meaning, yeah, it's true that in the worst case, quicksort will be order n square, but with probability like 0.99, right? The total quicksort will stop in just some constant times n log n. So, okay, so this means I should write it here. I have not written it here. So, if the paths are less, that means the depth is equals to this one, which means that probability that T of n is less than, say, 2.5 times n into log n by 4/3, which I will, I mean, just for the sake of analysis and for sake of representation, I will write it this way. This is more than 1 minus 1. Right? So this is the beauty of this probabilistic argument or randomized analysis. That quicksort is not only average complexity is n by log n, n log n, but it is also n log n for not the expected one, but almost always. So the worst case is happening only at a very extreme settings. Fine. Any questions so far? Nothing? Wonderful. Okay. Now in that case, tell me, how do we go about this one? How do you prove this kind of statement? Come on, someone should say it. Okay, let me ask you in a language that you guys are more familiar with. Okay, I toss a unbiased coin. N times. What is the expected number of heads? Tell me this one. What is it?
N
Am
by
I
2.
audible? Am I there?
N by 2.
This is n by 2, right? Then what is the probability that the number of heads is bigger than 1 plus delta into n by 2? Have you guys seen this kind of calculations ever?
Sir, expected number of heads by 1 plus delta n by 2.
Ah, good. So somebody told me that this is
Less equal
expected
to-
with n by 2, right? So this is less than 1 by 1 plus delta. You are completely right. This is true. Okay. Can you say, whoever told me, can you say what was, you are applying a theorem? What was the
Markov's
theorem?
inequality.
Right. So this is called Markov inequality. But see, Markov's inequality, what does Markov inequality say? Markov inequality says that for any random variable, probability that x is bigger than any number a, okay, any positive random variable, I should be careful. This is less than expected value of x by a, right? This is what Markov inequality says. This is for any random variable, any positive random variable x. But our setting, this is a very specialized random variable. What is the specialized random variable? Why is it specialized random variable? Because the number of heads. So if I write this EI is the indicator variable, okay, is the how do you define its indicator variable? What is the most common standard? I. The II is the indicator variable of the ith flip to be, or ith toss, right? Ith toss to be head. In that case, the number of heads, what is number of heads? This is nothing but summation of II, right? I equals to 1 to n. And these IIs are all linearly independent. Sorry, not linearly independent. They are all independent random variables. I was using terms from linear algebra. Yeah, okay, so these are all. So this is a much more structured object. In that case, can we say something? Okay. So I had told you a little bit on, I have given you 2 things to read. So I will ask you guys to go back and read it. There is the first thing that you can do, which is like the Markov's, but slightly more non-trivial. It is called the Chebyshev inequality. Please go and read it. For you guys, you really like it. Okay. Chebyshev inequality basically, of course, you possibly have seen it, is basically trying to understand it from the point of view of the second moment or variance, right? And then you can get something here, instead of this E of x by A, you can get it from the variance. And then the next one is the Charnov. A Charnov inequality, Charnov inequality. So this only holds for sum of linearly independent random variables. Okay, and basically what it says is the following. This is very interesting, by the way. Probability that, so sorry, maybe I should write it very carefully here. So if x equals to summation of, or we will just say, if A is equal to summation of xi, when xi's are independent. Hello, am I here audible?
Yes, sir.
Unequal, what am I talking about? Are independent. Actually, let's for the heck of it, just make this one II. Okay, and say 0, 1. You don't need to 0, 1 random variable. Okay? You don't need it exactly 0, 1. There are other non-trivial ones. I will talk about it just now. But let me just write it here. Probability that A minus expected value of A is bigger than delta times expected value of A is less than e to the power, forget it, let's call this one, bigger than A is e to the power a square by n. I think it's 4 times a square by n minus. So if you do this, all these calculations and all, what you will realize is that in the number of heads, okay, probability that the number of heads in the coin toss is more than n by 2 plus say 4 times square root n, this itself is less than any small number, say 1 by n. Okay, in fact, you can do it much more. Actually, it can be made to be in, this is probability is equals to e to the power n, e to the order n, I would say. So, see, I mean, if you have not seen this one, this is something that can really excite you. That not only when you are tossing coins, not only is the expected value equals to n by 2, but it is this close. Can you imagine? That means if you are tossing 100, in fact, you don't need this fourth thing also. I think you can remove get rid of this 4 also. You do this whole calculation properly. So what it means that if you are tossing 10,000 coins, okay, yeah, on average you should get 5,000 heads, but almost always you can say that chances that you are getting more than 5,100 heads is very low. And similarly, the probability that you are getting less than 4,000, 5,000 minus 100, whatever that number is, that many number of heads is also very low. So this is called Charnov bound. And the kind of, in the, I will just share this, in this thing that has been shared, in, you can see this notes that are there. This is the one that is shared about the probability spaces, okay, in the, from the web page. Please go over it carefully and you will see these beautiful applications of Charnov bound and Chebyshev's inequality and what can be done, and the proofs of them, and so on. Now, there are even more stuffs, okay? There are even more stuff. For example, you don't need them to be IID, you don't need them to be 0-1 random variables, but that requires some more non-trivial work, and I don't know whether you guys have read it or not till now. Have you had any course on martingales?
No, sir.
No, okay, fine. So whenever you do some course on martingales and all, you realize that these are special cases of something called the Azumah's inequality. Okay, but this is much more complicated. So you need martingales and all, but Charnow bound and all, they are very simple. The whole proof, the whole deduction of Charnow inequality, Chebyshev's inequality has been, and the Markov inequality, all the proofs are there in that note. And you can see how nice is this bound comes out. So it's a much more stronger. You can see this is much more better than what Chebyshev or what Markov was giving. Okay. So Markov was just saying something like, oh, it's the probability is 1 plus delta is less than 1 plus delta. It's like very small, very large probability, right? And the concentration is also very bad. And now we can talk about up to square root n. So you guys have never seen this kind of calculation before?
So we have seen Markov's inequality and Chebyshev, but like the application wasn't so good.
And Charnov also you have not seen.
Chernow, I think, was mentioned, but that was it. It wasn't proved.
But Charnov was actually done at the very end, last day of the semester in second semester. So we just know it, and it was also an exam problem. So we do not have much exposure to Charnov problems.
Okay, okay. Okay, so I really request you guys to go over them, and you can see this beauty of it. Okay, and in fact, now I should complete or close this lecture. Okay, so this one, whatever is written here in the red box, that follows from Charnov's inequality. In fact, you don't need it to be 2.5. I mean, you go and do the calculation. You will understand. Okay, you can do much better than 2.5. You can do a lot of things, and you can have some pretty nice results there. Okay, and note that this Charnov is kind of essential because with Markovs and all, you don't get 1 by n square. And if you don't get 1 by n square, you cannot apply union bound and obtain this result. Okay, so now I should say that I gave you one proof of the analysis of the expected value, and I continued with it for the concentration. Okay, in most of the books for quicksort, they only gives how to deduce the expected value and not the final concentration stuff. So what I have done is that I have in the web page given you 2 links, okay, for 2 write-ups, pretty nice write-ups. In one write-up, they can see only the how to calculate the expected value. There are 2 or 3 different approaches for finding the expected value. Okay, you can go and read them and see it. And then I have also referred to our slides. Okay, slides there. There actually this very nicely this bound, this concentration bound has been defined, described, and how we can prove that quicksort with high probability has runtime less than some order of n log n. Okay, I don't think I will give you a separate videos of this because this is a bit technical. So instead of video, I thought that by describing you guys with you guys whatever is going on here and giving you reading materials, that might be better off. I really expect you guys to be excited about it because this is more closer to whatever you guys are specializing, right? This is the yeah. So yeah, so tell me. So I have already given these links to on the web page, so you can might be find it out also. But in the meantime, I will also upload this video just as soon as the class gets over. Video of this lecture, so you can go over it if you want. But I will be happy to take some questions if you guys have any. No questions? Okay, so just before I recap, okay, so we have this quick sort, and then we had this randomized quick sort, right? Now what are the properties of that? It had worst case runtime order n square. The average or expected case runtime is order n log n. It is almost always order n log n, and the space complexity is order of 1, right? So the next question that we will be asking, and this is something that possibly I will upload a video on that, is there an algorithm that can have the worst case runtime order n log n, at the same time have order 1 memory, extra memory, something that we have not seen till now, right? And we will be describing you one such algorithm, and that would be a bit more going into a slightly different area of more data structure oriented stuff. So I will do a video on that and post it. Okay. So, any more questions? Any questions? Nothing?
No, sir.
Yeah. So if there's no questions, then okay, let's stop now. I think a quiz or assignment will be posted sometime the weekend or something. Okay, and it will be related to sorting stuff that we do.
So,
Yeah.
so what is the marking scheme for this course? Like, how many assignments are we expecting?
Honestly speaking, I don't have any idea, because I have not got any knowledge from the dean's office about how to work out this kind of stuff. See, there is no mid-sem and there will be an end-sem. How much marks will be assigned to the mid-sem, how many marks is not there, or how many marks will be assigned to the end-sem, and how will the quizzes and all be evaluated, and how much marks will be given, I have no clue. Okay. So unless the dean's office gives me a slightly more clearer idea, I will not be able to say anything. So I would say that instead of that, please take all the assignments that we say, which is for submission, seriously, because there's a high chance that that might actually end up becoming crucial in the final marks. But otherwise, that I have no idea. If you guys hear anything from the dean's office, please let me know.
So, like, Arnab sir has already given us a breakdown for the
What are they
marks.
given?
So he has given about 20 for projects, 10 for assignments, and 70 for mid-sem.
Mid-sem or end-sem?
Sorry, end-sem, end-sem.
I have not seen anything. Maybe that will be how it will be. Okay, in that case, that means I'm assuming that 30 marks will be there for this assignment and projects and all together, and 70 marks for end-sem. So,
like, I thought the teachers normally decided.
No. Usually, the amount of marks given for end-sem is more or less fixed. I mean, there's a slight 10% marks here and there, but they kind of, it is the dean's office thing that kind of stops off it. And that 30 marks or 30% marks or something, that will be in our hands, how we want to split it up.
Okay, sir.
Yeah, I have not seen hard anything, so I will just, yeah. See, I mean, I usually try to end up doing things which will help you guys in getting more better grades. Maybe I will take best of the, some of the best assignments and so on and so forth, and try to improve that grade and all. But yeah, at this point, I cannot say anything more constructive. I don't even know whether MSIM will happen or not. We have no idea how to have an MSIM. The Dean's office is still hoping that you guys will return to campus before the MSIM. So, yeah. Yeah, hopefully things will be clearer with the next sometime.
Sir,
Yeah.
can you please explain the expectation, that part, that expectation of length of path containing x is 2 log n? That part I missed a little bit at the.
Okay. So what does a path mean? A path means that every time you're picking a pivot and you're partitioning into two parts, right? Fine. So every time you pick up a pivot and partition it, it might not split up into some nicely into some fractions. But I say that if you end up picking up a pivot, where is it? If you somehow manage to pick a pivot which partitions the what is it called? Yeah, which kind of partitions this stuff into which is basically between n by 4 and 3n by 4, then I call that one to be good. Okay, a good pivot. Okay. So what we have seen, or what you can quickly prove, is that if I end up picking log n base 4 by 3 good pivots, then the size of the array containing x, right, it will go down by a fraction of 3/4, at least 3/4 every time, maybe even more. So that means in this many number of times, this many number of, after you pick this many number of good pivots, okay, at most this many number of good pivots, the size of the array containing x will certainly become 1. It might stop before that, much before that, but it's an upper bound. Okay, so all I need to do is that I need to pick up n by 4, n log n base 4 by 3 number of good pivots. Okay, and what does a pivot mean? A pivot is a particularly randomly chosen index, right? A randomly chosen index is the same way as saying that I can randomly choosing an element from the array. Right? Now here is the elements of the array ordered in the increasing order. Okay. It is not how the array is, but I'm just, for the sake of our calculations, I'm writing it. It's added in the increasing order. And if that element that we have picked out, which is a of I, is between this n by 4 index and the 3n by 4 index, right? Then I know that this is a good pivot. So since I'm picking up a random I, so the AI that I have is also a random element in this whole set from A1 to AN, which means that with probability half, I would get a random element, with probability half, I will get a good pivot. Okay. So all I need is this many number of good pivots at most, and I know with probability half, every pivot is a good pivot, kind of stuff, right? With probability half, the pivot is a good. So that means the total number of things, if the length of the path is more than twice this, right? Then what is the expected number of good pivot that you get? Is this quantity, right? Because 2 times log n base 4 by 3 into half is this much. So that means the expected length of the path would be less than, I'm not saying exactly equal, but less than 2 times log n base 4 by 3. Okay, the expected length will be less than 2 times log n 4 by 3. So I'm not exactly counting the expected length, but I'm kind of coming up with the upper bound of that. Is it clearer? Hello?
Yes, sir. Yes.
Yeah, so as I told you, there are a link that have been posted in the web page. There, I think there are two other different ways of calculating the expectation. Okay. So if you just are interested in proving the expectation of 2 log n, then that will be a kind of a thing that you can do. Okay. You can read this. And also I posted a set of slides. So none of them are mine. It's from some other people's lectures and all. So there you can see the concentration also. Okay. Any more? No? Okay, in that case, let me stop now. And I will upload the video shortly. Okay. So, okay, see you.